Alrighty, guys, we should be starting at the daily agenda, and actually realizing was in the process of fixing this up. We should work through the day three notes, work through that functions day three self-assessment, and once you complete the notes and you get to the self-assessment, if you even have time, get to that portfolio afterwards. But today, what I want you guys working on is getting through the day three notes, and then after that, really just chipping away at whatever you haven't gotten to yet with regards to the day 1, 2, or 3 self-assessments or portfolios. Okay, by the end of the weekend, we should have all that stuff done. I threw this image in here. If you ever get confused at any point during today's notes, hit pause and come back to this image. I think this image really it makes sense of a lot of things. So let's get started. All right. So looking at the day 3 notes, we're looking at what's called continuous versus discrete functions. All right. So think about what you may think of when you hear continuous. Continuous is something that doesn't ever end, right? There's no pausing. There's no beginning, there's no end. It's continuous, right? It goes on and on and on. Discrete, to be discrete about something means to kind of be reserved or kind of quiet about. So that's actually not quite the definition we're going towards. In math, discrete is actually going to mean, if you look at the daily agenda, discrete is when it doesn't make sense for there to be something between 2 points. So like if we look at the number of cars sold, one car is going to cost 20 grand. Cars are very expensive. 2 cars, therefore, would cost 40 grand, right? But you can't sell 1.5 cars. It's either you sold 1 car or you sold 2 cars. There's no such thing as 1.5 cars. But if you look at the number of pounds of grapes sold, I know that's totally random, but number of pounds of grapes sold, you could potentially have something between 1 and 2 pounds. You could have 1.5 pounds. You could have 1.6, 1.7, 1.8, 2, 3 pounds, right? So that would be continuous. There is actually something between 1 and 2. So when we go back here, just looking at what continuous and discrete means graphically, that should help. So looking through the learning goals, I can determine when a discrete model or a continuous model is most appropriate. Okay, that's the first and foremost learning goal today. What is the difference between discrete and continuous functions? I feel like we already kind of answered both those first 2 questions. How can I tell if a discrete or continuous model is best for a given situation? We'll chip away at that a little more. And are all linear functions continuous? Are all arithmetic sequences discrete? We'll consider that. And be able to use a table to find the first difference to determine if a function is linear or not. Okay, so go back to that as you work through today, and make sure that you're accomplishing those things and you're able to master those goals. Now, if you want to pause and go and look up what does discrete mean in a graph in math, what does a continuous graph look like in math, what is a first difference in math? Actually, we already talked about first differences, right? It's just a common difference. Honestly, if you wanted to take this picture, copy it, and just paste it right in there in the vocabulary, that wouldn't be a bad idea either. But go ahead and fill in that vocabulary. And then whenever you're done there, we'll get going on the example number 1. All right, for example number 1, I know it says partner activity. I always encourage you guys to work together, so feel free to work with a partner or in a group. Scenario 1, the Library of Congress in Washington, D.C., is considered the largest library in the world. They often receive boxes and boxes and boxes of books to be added to their collection. Since books can be quite heavy, they aren't shipped in big boxes. So on average, each box contains about 8 books. So if on average each box contains 8 books, how many books are received by the library in 6 boxes, in 10 boxes, in n boxes? Why don't you try coming up with a sketch of a graph and see if you can come up with an equation for this, okay? Try to put that equation in function notation and in slope-intercept form like we talked about in class yesterday. Pause this video and give it a try on your own right now. All right, so now let's consider this. So I plotted the point 1, 8, 2, 16, 3, 24, and 4, 32. Now, like when we're talking about the number of boxes, right? You can have one box, you can have two boxes, you can have three boxes, but you can't have 1.5 boxes or 2 3/4 of a box, right? It's either one box or two boxes or three boxes. So this one wouldn't make sense to connect the dots, right? This is going to be what's called, I'll type this out. This is what's called a discrete function. Okay, now when we write an equation for this, we're going to want to write this in function notation. So let's go f of x is equal to, what was the slope again? It's rise over run, and our rise over run is 8 over 1. But let's just put 8. No need to put over 1. So 8x plus, if we have 0 boxes, or if we have 0 boxes, how many books are we going to have? Well, 0. So we're just going to cross that x, the y-axis, our 0th term, at 0. So our function is just simply going to be f of x is equal to 8x. All right, now scenario 2 is a little bit different, right? So many of the books at the Library of Congress are electronic. About 1 ebook can be downloaded onto the computer each hour. If 13 ebooks can be downloaded onto the computer each hour, well, that doesn't make sense. What is that? I think that was already crossed out in your guys' notes. This doesn't make sense. Cross that out. Okay, so many of the books are electronic. If about 13 ebooks can be downloaded onto the computer each hour, so that means 13 after 1 hour, 26 after 2 hours, 39 after 3 hours, etc. How many ebooks can be added to the library in 3 hours, 5 hours, or n hours? Well, think about like a loading bar, right? When something's downloading and it's like taking forever, it's like the spinning wheel, right? This thing, when these books are being downloaded, you can actually have half of an ebook downloaded. You can have 1.25 of an ebook downloaded. You can have 3 of an ebook downloaded. You can have 3.2, 3.5 of an ebook downloaded. So this right here, this is what's called a continuous function. So this we can actually continue through with a line, right? Because all the points in between the line also count as well. At a certain point, we are going to be right here at about 2.8 books downloaded, right? So we'll have part of a book downloaded. These are not like complete books in boxes. So a little bit different. Now, when we consider the equation here, very similar. And you can see, look, the line went right through the y-intercept at 0. This one would be f of x, f as a function of x in function notation, is equal to, well, what's our rise over run? Well, it's about 13 books per hour. And you can go back and you can zoom in here and take a look. It looks like we are rising 13 and running 1, rising 13 and running 1, rising 13, etc. So what we have here is a slope of 13 over 1, or just 13. Remember, we don't need to put the over 1. So f of x is equal to 13 over 1x plus the 0th term. And the 0th term is just 0. So you can literally just put 13x. Now, if you wanted to evaluate this and find out how many books there were after 5 hours, simple, real simple. All you have to do is f of 5 and then crunch the numbers here and just do 13 times 5. 13 times 5, use calculator. Off the top of my head, 50, 65, I guess that is. So there would be 65 books downloaded after 5 hours have passed. All right. So that right there is what's called evaluating your function, using your function. All right. So would it make sense in either of these scenarios for there to be a time when 32.5 books have been downloaded into the computer or placed on a shelf? This makes sense when we have a continuous function like the ebooks, but this does not make sense when we have a discrete function like boxes of books. All right. So make sure that makes sense to you. Again, please pause this, okay? Consider kind of what you've been doing so far. And before you go down and look at what I've got here for example 2, give it a try on your own. Okay, give it a try on your own and then cross-check it. All righty? All right, now thinking about our little sister Savannah is 3 years old. She has a piggy bank and she wants to fill it. So she starts with 5 pennies. Stop there. So she starts with 5 pennies. That's where this is a little bit different than the last one. In the last one, we were starting with 0 books, but here we are starting with 5 pennies. So before we even start counting, before a day has passed, we already have 5 pennies. And each day, she's adding 3 pennies to the piggy bank. What this is going to look like is this, and it helps to have tables. On the 0th day, so before a single day has even passed, there's already 5 pennies, right? But now we start implementing this common difference of 3, and you can see that our 0th term is not 0 like in the examples above up here, right? Our 0th terms are not 0. Our 0th term here is 5. So we're actually going to start right here on the y-axis at 5, and then we're going to rise 3 pennies for every 1 day that passes. Rise 3 pennies for every 1 day that passes. Rise 3 pennies. You can go on and on and on and on and on, right? As long as this happens, as long as we keep throwing pennies in the piggy bank here. So when we're talking about an equation, let's think about this. We're going to put this in function notation. F of x is equal to mx plus b. Think about again what m stands for. Well, remember m is slope, and slope is the same thing as the common difference, and the common difference is 3. Okay, plus what is b? B is our y-intercept, or in other words, our 0th term, and that's 5. So 3x plus 5. So if we want to know how many pennies she's going to have on the 3rd day, we already know it's 14 in the table here, right? But we can evaluate this and say f of 3 is equal to 3, and we're going to plug in 3 for x, plus 5, oops, not percent, plus 5. And if we just kind of work our way through this thing, 3 times 3 is 9, and 9 plus 5 is equal to 14. So we can evaluate using our function, and we just confirmed that this equation must be correct, 3x plus 5, because when we plugged in 3 for x as the input, the output was 14, and that matches our table. Now think about this. Is this going to be continuous or discrete? Can you have 8.5 pennies? No, it's either 8 pennies or 9 pennies. You can't have 8.5 pennies. So this would be a discrete function. Go ahead and give that next one a try as well. All right, now think about this one. Our family has a small pool that holds 1,500 gallons of water. That piece of information is irrelevant at this point. I decided to fill the pool for the summer. I was getting bored just standing there watching the water flow. Think about the water flowing, right? That water's not flowing and stopping, flowing and stopping, flowing and stopping. It is not discrete. This should, flags should be flying, right? Like you know this is a continuous function. The water continues to flow and flow and flow and flow. And began to think about a mathematical model for the time it takes to fill the pool. Now we know that it fills at a rate of 2 gallons every minute. Okay, 2 gallons every minute. That sounds like a slope to me. And we only started counting once we were at 5 gallons of water in the pool, right? So we only started counting at 5. So at 0 minutes, when we hit the start button on our phone to start timing this thing, it already had 5 gallons of water in the pool, right? And slowly but surely, this water keeps on getting added and added and added until it hits that maximum amount of whatever, 1,500, right? Let's not worry about that for now. But what you can see here is this will be a continuous function. But same thing applies. We're rising 2, running 1. Rising 2, running 1. And remember, yesterday we defined that as our slope. So if we're going to come up with an equation, in f of x is equal to mx plus b form, where m is the slope or the common difference, then we know that this is going to be 2x, right? Because the m is our common difference, and which is also known as our slope, and our slope is rise 2, run 1, so 2, plus our 0th term, or what we basically what we start with, right? So at 0 minutes, there were 5 gallons of water in the pool. So our function is going to be 2x. F of x is equal to 2x plus 5. All right, let's wrap this up with example 4. So when you see a graph or rewrite an explicit formula for an arithmetic sequence, it is apparent that it represents a linear function. I mean, that's what we've been talking about the last 2 days. However, the structure of a table requires other strategies. So One strategy is to examine what's called the first difference. First differences are the values determined by subtracting consecutive output values. So like 10 minus 6 is 4. 6 minus 2 is 4. 2 minus negative 2 with the double negatives is 4. 4 minus 3 is 1. 3 minus 2 is 1. 2 minus 1 is 1. So it's just finding those differences and writing them down, kind of like we see in these two examples here. So if the first difference of a table of values are, let's say, constant, meaning like 4, 4, 4, right? If it's constant, then the relationship is linear, okay? So these obviously are both constant, right? This is right here. This is continuing on. Plus 1, plus 1, plus 1, plus 4, plus 4, plus 4, plus 1, plus 1, plus 1, plus 4, plus 4, plus 4. It's constant, therefore it's linear. So let's check A, see if this is linear. Plus 1. All right, nice. Plus 1. All right, nice. So far, so good. Plus 1. It checks out. Okay, 12 plus, from 12 to 15 is plus 3. So it should continue on plus 3. From 15 to 21, 15 to 21, that's 6. And from 21 to 30, that's 9. This is not linear. Okay, and it's not linear because, go back up here, the differences are not constant. Are not constant for the y values. Okay, let's check the next one here. On B, it looks like we're adding 1, adding 1, adding 1. It checks out so far. We're subtracting 4, subtracting 4, subtracting 4. This one checks out. Okay, because it's constant on both sides, this is linear. The differences for both x and y are constant. Therefore, it's linear. And you can always throw these points into a table on Desmos just to make sure and look at the points and as they show up on a graph. And you'll be able to see like, oh, yeah, that's linear. Or, well, that point actually does not fall in line. Look at the last one here. Plus 1, plus 1, plus 1 checks out so far. Plus 3, plus 5, plus 7. So this one actually has a second difference of 2 plus 2 plus 2. But remember, we said this right here, second differences, those are actually quadratic, and that's not, you're not going to learn about that until IM2. So don't worry about this quite yet. For right now, at least, though, we can tell that the differences here are not constant. Therefore, this guy right here is also not linear. Okay. What characteristic of a linear function is the constant first difference? Well, holy cow, we talked about this a ton yesterday, right? First differences are just a common difference, right? And we know that a common difference is the slope, okay? So we now know of a linear function, the first differences are the common difference, which is the slope. All right, guys. Again, sorry I'm not here today. I hope you had a great day and have a great weekend. Get caught up on that work, get caught up on rest and sleep, and I'll see you Monday.